we'll take a look at some classifications of compound propositions. And the reason that we might want to do that is it's pointless to argue if you agree. So how do we know if we're in a situation where our arguments are equivalent? How do we know if there's nothing to disagree about? And how do we know if we even need to explore any further, because the proposition will always be true or always be false, and there's no need to explore any further? So let's take a look at some classifications of compound propositions. If we have this compound proposition P, it may be made up of many different atomic propositions, some smaller parts that are added together. And the truth value of the variables that make up those parts are going to determine whether or not this greater compound proposition is true or false. And sometimes, no matter what we do with the smaller pieces, it will always be true. Sometimes it will always be false. And sometimes it matters. So let's talk about those three situations. Always true, always false, or it depends. If the compound proposition is always true, then it is called a tautology. And what that means is no matter how you assign truth values to the atomic propositions that it's comprised of, the compound proposition will always be true. Every single row of its truth table will end in true. There are other compound propositions that will always be false. If it's always false, no matter how we assign those truth values, then this is called a contradiction. And finally, there are times where it has to be determined. So there are combinations of truth values that will lead it to be true, others that will lead it to be false. And so those atomic proposition truth values, they matter. This is called a contingency. So let's take a look at a few examples of those. Examples of tautologies, contradictions, and contingencies. So can you identify or categorize the following? P and not P. So if we create the truth value for P and not P, we know that if P is true, then not P is false. If P is false, then not P is true. And so we can complete that portion of the truth table. What does that mean for P and not P? If we look at the combination, the conjunction of P and not P, we see that there's no possible combination that will lead P and not P to be true, because we can't have P be true at the same time that not P is true. And so because of that, every possible way that we're able to assign truth values to the atomic propositions that make up P and not P lead us to false values. So P and not P is always false. And so this is an example of a contradiction, right? P and not P is always false, no matter how we assign that. Let's take another look at an example P or Q. Well, I'm not even going to create the truth table for this, but we've seen examples in the past where we look at P or Q, and we can choose to look at combinations where it depends if P is true or Q is true, right? If P and Q are both false, this statement is false. If P or Q is true, we know that this proposition, this compound proposition P or Q is true. So it really does depend. It depends. And in fact, because it depends, this is considered a contingency. Then let's look at P or not P. And if we carry on with our truth table, we know that P or not P is true if either P is true or not P is true. And so going down the rows, we see here P is true on the first row, so P or not P is true. And on the second row, we see that not P is true. And so P or not P is true. And so in every possible case, no matter how we assign the truth values, P or not P is always true. And because that's the case, that means this is an example of a tautology. So now, if we have these classifications, how do we know if we have propositions that are logically equivalent? And what that means is stating one is the same as stating the other. And the way that we check that is if P, if and only if Q is a tautology, they're logically equivalent. And in fact, we have a special means of denoting that. If two propositions are logically equivalent, then we write that as P is equivalent to Q. It looks like an equal sign with an extra line above. So that equivalency is what we're checking for. And how do we check that? Well, we can use truth tables, which we've done throughout. Compound propositions are logically equivalent if and only if the columns giving their truth values agree. So if P is equivalent to Q, then if I have a truth table, when P is true, Q is true. When P is false, Q is false. So all of this brings us to the concept called satisfiability. And what is satisfiability? Well, when we consider compound propositions, something is satisfiable if there's a way that we can satisfy the proposition. And what that means is there's an assignment of truth values to its variables, its atomic propositions, such that it is true. There's some way that we can make those propositions true. If the proposition is a tautology or a contingency, it is satisfiable. If there's no way to make them true, if it's a contradiction, then it is unsatisfiable. And this can happen if a compound proposition is false for all possible assignments of truth value. It can never be true. So if our compound proposition is a contradiction, then it is unsatisfiable. So let's take a look at our previous examples. We saw that P and not P was always false, so it was a contradiction. And in fact, that means that is an unsatisfiable proposition. That's a compound proposition that can never be true. And so that we can see in our truth table is always false. There's nothing we can do to change the fact that P and not P will always be false, no matter how we assign truth values. So this is an unsatisfiable proposition. P or not P, we can see, is always true, as shown before. And so this is satisfiable. In fact, it will always be satisfied. And then finally, when we look at P or Q, we said this is a contingency. It depends on the truth values of both P and Q, but there are ways that we can satisfy this. There are ways that we can lead to P or Q being true. If we let either P or Q be true, P or Q is also true. And so this is satisfiable. And what we've seen is we've been making use of truth tables so far. And so what happens when the number of variables grow? What if the number of atomic propositions needed to determine the truth or satisfiability of this greater compound proposition is so great? So this can certainly happen. Using a truth table can be done by hand for compound propositions with a small number of variables. But what happens when that number of variables grows? This can become impractical. For instance, we see that when we have one variable, there are two rows within our truth table. If there are two, P and Q, we have 2 squared or 4 rows in our truth table. Once we have 3 variables, now there's 2 to the cubed or 8 rows in our truth table. What if we had 20 variables. Now we have over 1 million rows in the truth table for this compound proposition. This is entirely impractical to do by hand. At the moment, there's no known procedure for solving whether or not a given compound proposition is satisfiable for a large number of variables in a reasonable amount of time. There are smaller problems, such as solutions for a Sudoku puzzle that are able to be obtained, satisfiability problems of a lower scale. However, we'll look later to explore how important the role of propositional satisfiability is and how it plays a role in the study of the complexity of algorithms. But for now, we'll stick with this basic definition.